The last new material semester cannot end soon enough. Right. So the cool root finding methods, and by cool I mean more rapidly converted than what we've seen so far. First, on the announcement side of things, so the final exam for some take-home formats similar to a midterm. So make sure that it is posted in Canvas by this time of the day, the Monday of finals week. As upper bound on the upload time.
Reminding us of something that has to be forgotten. Well, not yet, but
Rappers.
Yeah.
And
Doing another diary today.
not today. And this is the due time, the last day of finals. That is also the date and time by which any other work needs to be submitted.
December 7th.
Yes. Because final grades are due in SOAR on the morning of December 11th, and you need time to grade whatever's left. Well, I have a backlog of grading now that I am slowly working my way through. But I know that an avalanche of assignments is going to come my way. Some people have turned in a lot, and some people not so much.
Still catching up on concept shit.
So, well, a lot of people are. So please keep that in mind. But also the lowest two assignments, homework should is hard. Okay, so now getting again with root finding methods. Newton's method. Now, we've seen with other problems that we considered this semester that a good way to develop algorithms for solving various problems is you first ask what kind of input is a problem particularly simple to solve. Now here we're interested in finding roots of a function. So the easiest function to find a root of is a linear function. A line that is not a horizontal line has a unique x-intercept. So if this is our function, so written in point-slope form, so it's a line of slope m passing through a given point x naught y naught, then we go ahead and set this equal to 0, and then we go ahead and find the root, x star. So the x-intercept, if I just set this equal to 0 and solve for x star, then this is what I get. X star is equal to x naught minus y naught over m. But if I think of y naught as f of x naught, but this is the equation of a line passing through a point, x naught y naught. And then m, the slope of a line, well, that's a derivative, which is a constant in a linear case. But so I could think of this x-intercept, x star, as x naught minus f of x naught over f prime of x naught. So that's going to be helpful to us in terms of finding roots of more general functions. So now that we see, this is how we solve the root finding problem for the simplest possible case, linear function. Now the second question we pose is, how can we use that knowledge of how to find a root in the simple case to find a root in more general case? So just to draw a parallel with other things we've seen, how do we solve a problem with numerical differentiation or integration? Well, we consider the simplest case, where your function you're taking a derivative or integral of is a polynomial. Those are the easiest ones to work out. And then how do we numerically integrate or differentiate a general function? you approximate it by a polynomial and you solve a problem for that case. So that's what we're going to do here. If we're trying to find a root of a general function f of x, what we do is we approximate f of x by a linear function and then get the root of that. But the question is, how do we do that? What is the best linear approximation to choose? So one way to do that is if we pick 2 points on the graph of f, then we get the equation of line passing through those 2 points, and that's called a secant line. We can find the x-intercept of that. That is one approach that we will look at more closely later. Or if we consider just 1 point instead of 2, if we approximate f of x near that single point x naught by a line that matches f at that point, but also the slope of a line matches the derivative of f at that point. Well, that would be a tangent line approximation. And that's, and this is a tangent line, this is the equation of a tangent line. So y is f of x naught plus f prime times x minus x naught. So now, if I set y equal to 0 and solve for x, so the x-intercept of a tangent line is exactly this, which is the same formula that we saw earlier for just the x-intercept of a linear function. So, now I can say that this x star, which is the exact root of the tangent line of f, can be taken to be an approximate root of f itself. Now, I'm not saying it's necessarily a good approximation, but it is an approximation nonetheless. So now, what I could do is I could organize an iteration around this concept. So let's suppose I have some initial guess. I'll call it x superscript 0. So then, I use that initial guess and compute the x-intercept of a tangent line of f at my initial guess. And this is, so once I have an x-intercept, I'm taking to be a new guess of a root, presumably a better one. And then I can keep going. So I could now take the tangent line approximation of f at x1, and then use this formula to compute a new iterate x2. That should be getting closer to the root. And then I keep going. So now I have an iteration where with each iterate, I get a new tangent line approximation, compute the x-intercept of that, and the idea is this should be getting closer and closer to the root. Because the closer you are to a root, because remember, a tangent line is a pretty good approximation of f, at least locally, near a point of tangency. So if xk is already fairly close to a root, and then I take the tangent line, then that tangent line should be, its x-intercept should be a better approximation to a root. So this approach of choosing the initial guess, x0, and then using this formula to continually produce new iterates that hopefully will converge to an exact root of f, that is called Newton's method. So Newton's method is based on the idea of approximating f by a tangent line, finding the unique x-intercept of that tangent line, and then repeating. So, questions about how Newton's method came to be?
So it's that idea of turning a problem into a root finding problem again. Like thinking of how you can construct a problem for which x is the, oh, I'm sorry.
Well,
Yeah, so the idea, well, that,
okay.
it's the idea that we were discussing for one of the explorations,
Right.
the intermediate balance theorem.
Okay, yeah.
Yeah, like, but, like, it's not rearranging, but it's the reasoning.
Okay.
Like, the x is the root and, like, setting it equal to 0.
Yeah.
So, no, I think please, yeah, disregard whatever I said.
Okay.
I'm saying things that are non-existent.
Okay, but you're still filling me in later.
No, really, I was
Okay.
trying to.
Like
look
the wonders,
up,
yeah.
and,
All right. Okay. Now, does this method work? And if so, how well does it work? So this we're going to perform called a convergence analysis. So the idea is we want to express the error after k plus 1 iterations in terms of a previous error that we got after k iterations. So what I'm doing is I start with xk plus 1 and I subtract x star. So this is the error after k plus 1 iterations. Now, all I've done at this point is I'm replacing xk plus 1 with the Newton's method formula, and I'm still subtracting x star. So now I want to get a handle on trying to manipulate this expression to involve the previous error, xk minus x star. And a way I can do that is through Taylor expansion. What I do first is, in the numerator, I just subtract f of x star. Because remember, f of x star is the root. So f of x star is 0. So I literally am subtracting 0 up here. But I'm doing that to set up the use of a Taylor expansion. And then what I do is, if I'm taking a Taylor expansion of f of x star with the center being xk. So this part of square brackets right here is a Taylor expansion of f of x star centered at xk. Now, what happens though is first we have these f of xk's right here will cancel. But then what will happen is, if I look at this part, f that has f prime of xk, here the f primes will cancel, and then I have x star minus xk. But this x star will cancel with this one, and this xk will cancel with this xk. So in other words, everything here, almost everything here, is going to cancel. I can take my word for it. The only thing that doesn't cancel is this term right here. So the 1/2 second derivative times xk minus x star squared, and we still have this derivative down below. So it simplifies to this. Now, notice the error after k plus 1 iterations is equal to this fraction times the previous error squared. Very important, because that means that Newton's method is quadratically convergent. So this is the first method that we've seen in this chapter that shows quadratic convergence. Now, I did mention when I covered fixed point iteration, fixed point iteration generally is linearly convergent, but if you're solving x equals g of x and if g prime happens to be 0 at the root, then you do get quadratic convergence in that case. But again, that's an isolated case. But here, presumably we get quadratic convergence in general, at least as long as this derivative, f prime, is non-zero. So actually, this is the asymptotic error constant. So it's f double prime at the root over 2 f prime at the root. So as long as f prime at the root is non-zero, we really do get quadratic convergence. So questions about the convergence analysis? Yes.
So x asterisk, the asterisk is the true value, the
Yeah,
true
for roots.
exact, yeah.
Yeah, and since xk is presumably converging to the root, that's how we get x star down here. And in ck, that's the unknown point from a Taylor expansion. That is between xk and x star, but xk is converging to x star. So squiggly k is also converging to the root. But yeah, if f prime is 0 at the root, then we have a big problem. Okay, actually, I'm trying to recall. Okay. Which problems I assigned? Because from this section it's 3, 4, 7, and 8. Okay, yeah, right. This function. Okay, emergent behavior. And then problem 7, which was. And not everybody took this assignment anyway, because most people drop. Oh, right. Okay, Secant methods we'll talk about in a bit. Okay. Okay, so here's an example of where Newton's method does not converge quadratically. So my function f is x minus 1 quantity squared times e to the x. So obviously this function has a root at x equals 1. So if I look at f prime, so using the product rule, if I simplify as much as I can, I end up with this. So x equals 1 is a root of f of x and of f prime of x. In other words, x equals 1 is a double root. So since f prime of 1 is 0, this convergence analysis right here does not apply. So what Newton's method looks like in this particular instance, if I try to carry a similar convergence analysis, so I look at the xk plus 1 minus the true root, minus 1, then what I can do, after a lot of algebra, I end up with this, that the error after k plus 1 iterations is equal to the error after k iterations, but only to the first power, times this fraction. So what happens in this case is, if a derivative, because the derivative is 0 at the root, convergence degrades from quadratic to linear, and the asymptotic error constant turns out to be 1/2. Now, it can be shown, and this is actually in an exploration, but it turned out to be not one I assigned. That, okay, here I only showed in this example, we have linear convergence, asymptotic error constant 1/2. It can actually be shown that in general, if f has a double root at x star, so f of x star is 0, f prime of x star is 0, you generally get linear convergence, and the asymptotic error constant turns out to be 1/2. Now, it can also be shown that if the root has even greater multiplicity than 2, like if the second derivative is 0 at the root, making it a triple root, it's still linear convergence, but the asymptotic error constant changes. So that's true regardless of a function f. Okay. Now, can anyone tell me what is a method we already have seen that converges linearly with an asymptotic error constant of 1/2?
Isn't it fixed?
A fixed point is linear, but it's asymptotic error constant is not necessarily 1/2.
Iteration.
We haven't seen very many methods.
True. But
Yeah, because by section, the error is being cut in half.
yeah.
So you would think, oh, well, if Newton's method for this example is no better than, in terms of speed of convergence and bisection, then maybe we should just use bisection. But what is the problem with using bisection in this example?
This no change of sign?
Yeah, this function is non-negative everywhere. There's never a sign change. So yeah, you could not use bisection in this case. So you don't have any great method for this function, which is kind of tragic. But I mean, for these kind of problems where the slope of a function at the root is exactly 0 in this case, or even if it's near 0, that is an example of a root finding problem that is ill conditioned, that poses problems for whatever method you use to solve it. This is a property of a problem, not the algorithm. Now, one thing you could do, anytime you have, if f has a multiple root, x star, then what you can do is you can form this function, f divided by its derivative. So this function, x star is a simple root, multiplicity 1. So a derivative of psi prime would have a non-zero derivative at the root. So what you could do in this case is you could try applying Newton's method to this function instead. And then you would recover your quadratic convergence. The problem is, now you need to compute a derivative of psi. And if you compute a derivative of psi, this expression, using the quotient rule, then you need second derivative. So this is already one disadvantage of Newton's method compared to other methods. You have to have a derivative. Every iteration you're evaluating f at xk and also f prime of xk. What if f has a particularly complex derivative? That's extra computational expense. So sure, you can get faster convergence if you do this, but then you're also degrading efficiency further because now you need another derivative. What if you don't have the second derivative? What if f is not necessarily 2 times differentiable? So this is not, it's not some great cure. All right, so questions on this part and how Newton's method is not so great. Yeah.
If it's the case where f double prime of the root is also equal to 0,
Yeah.
then would you have to this again, the workaround again? Apply it again?
This workaround will help no matter what the multiplicity is.
Okay.
Let's think of it this way. Suppose x star is the root of multiplicity, let's say 6. So you think of f of x as having x minus x star to the 6 in a factorization of sorts. I know it's not a polynomial, but still.
Yeah.
Well, that means the derivative would have x minus x star to the 5th in this factorization. So then you end up, all those factors get canceled except 1. Now, on the other hand, let's suppose a function has a certain properties, like if f is always increasing and concave up, so the concavity never changes, it can be proven that no matter how far the initial guess, how far away from root the initial guess is, Newton's method is guaranteed to converge and converge quadratically. So there are certain cases where Newton's method behaves very well. In this case, if the derivative is not changing sign, so that's a favorable case for Newton's method. Okay. Actually, I should mention, regarding this example here. You actually saw an example of Newton's method in homework 1. Newton's square root dot m. That code computed the square root of 2 by using Newton's method to find a root of a function x squared minus 2. So that's a function that where positive x is always increasing in concave up. So in that code, the initial guess was chosen to be 1. But you could have chosen an initial guess of literally a million, and it would still converge to square root of 2. It would take a while, but it would do it. Now, I want to show what happens with that example, square root of 2. Should have it here. But not. And I have certain Newton's method examples here, but I thought I had that particular one. Oh, yes, it is here. Okay, so here to however many decimal places is the square root of 2. So when I use Newton's method on this function, the initial guess x0 is equal to 1. Then here's the progress of the iteration. This is what we saw back in the MATLAB tutorial. Over here we have the absolute error in these approximations. Notice the number of correct decimal places that we have. So in other words, number of zeros in a decimal expansion of the error. 1, 2, 5, a zillion, 11. Okay. The number of correct decimal places roughly doubles from one iteration to the next, which makes sense because suppose your error is like 10 to the minus 5. The next error should be proportional to that error squared. Well, you're squaring that error to 10 to the minus 5, and now you're getting 10 to the minus 10. So sure enough, the number of correct decimal places double. It's an approximate relationship, but it's one way that you can detect that there is a certain order of convergence. How many, at what rate do the number of correct decimal places in your approximation increase from one iteration to the next? And the thing is, in a floating point number system, you can only expect about 16 decimal digits of precision anyway. And if your number of correct decimal digits is roughly doubling, then 4 or 5 iterations should be all you ever need for Newton's method. So when it is working well, this isn't like bisection where you might have to perform like 50 iterations, or even fixed point. That was slowly converging too. When it's quadratic, you're done just like that. It's like lightning fast. So that's why we like quadratically convergent methods. Because then you can trust that you can literally count on the fingers of one hand how many iterations you're likely going to need. There are some methods that use Newton's method where they only perform one iteration. Now in that case, that's a situation where there's no point in iterating all the way to machine precision because there's other error involved. It would be a waste. But the fact that one iteration is needed just shows how effective Newton's method is. But it still has to be used with caution. And this example illustrates why. Newton's method in division. This is my favorite Newton's method example. So suppose we have this our function, a minus 1 over x, where a is some positive number. Now, the root of this function is x equal to 1 over a. So whatever a is, the root of f of x is a reciprocal of a. So then I go ahead and take a derivative, and that's just 1 over x squared. And now I work out what Newton's method would be. So here we have x equals 1 equals xk minus f of xk in the numerator, divided by the derivative of xk in the denominator. But then I simplify all this. And this is what I get. So this is my Newton's method iteration. And as mentioned, the root is 1 over a. So this iteration will compute 1 over a without performing a single division. So it's a way to divide without dividing. This was actually used to carry out division in hardware. I believe it was an old IBM computer, like from the 60s or so. So they did not have a division circuit. They had circuits for addition, multiplication, and subtraction, and division was carried out in hardware using this. Now it didn't last, but that shows because this rapidly converging, not many computations were needed. Now here's an example. I let a equal to 12, and then now the exact root in 1/12 is like 0.08 repeating. Suppose I choose an initial guess of 0.1. So I can show you what happens with the iterates. It's in the text. Yeah, here we are. Okay, so my initial guess is 0.1, and then I carry out 2 times the previous guess minus 12, the number I want the reciprocal of, times the previous guess squared. I get 0.08, so already that's 1 decimal place correct, a couple decimal places. Then I do it again, to get in closer, and then get very close still. So all it takes is 5 iterations, and I'm there to quite a few decimal places. So in that case, it worked very well. But now let's do it again. Initial guess of 1. And things don't go so well. The iterates become negative, that's already a bad sign, but also pretty large, and again, larger. It diverges very rapidly, so pretty catastrophic. So the performance is quite sensitive to the initial guess. Okay. Now to give you a visual idea of why, okay, here we have the graph right here. So here we have, this curve is part of a graph of 12 minus 1 over x, and then this is the other part of a graph, because there's going to be an asymptote at x equals 0. So what happens in this case, okay, so this circle right here is at wait. Okay. I feel like something's wrong with this picture. I better check. Okay. So in this case, where initial guess is chosen smaller, the tangent line ends up getting me closer to the root. I'm sorry. Okay, this picture is for a slightly different example. Instead of a equal 12, it's a equal 8. I really should change that. Okay, so here the exact solution is 0.125. So here, this circle right here is my good initial guess, 0.1. I compute the tangent line, which the tangent line is closely following the graph of a function. And what happens is I get a good approximation to the root. Now, on the other hand, if I choose my initial guess over here, x naught equal to 1, then I compute the tangent line, and notice the tangent line has its x-intercept way over here. So I end up on the wrong portion of the graph of my f of x. And then we get divergence after that. It's all pretty hopeless. So the problem is, and I'm choosing a positive initial guess, I need to make sure that my iterates remain positive if my iterates, as long as my iterates remain positive, then I should get convergence. So how do we guarantee that? Well, if there's any questions about the behavior of a graph. So here we have good tangent line, this vertical one, and then bad tangent line over here. So you get an idea as to why if we're too far away from the true root, this is going to go badly. So here's what I can do. I want xk plus 1, which is given by this formula here, I want it to be positive. So then, if I require this to be positive, and then simplify, I need xk to be, okay, I want it to be positive, and I also need it to be less than 2 over a. Now, if it turns out that xk is happens to be also greater than 1 over a, I will have a decreasing sequence of iterates that will converge to the root. Now, so here's the where things get kind of crazy. This sounds like a terribly impractical criteria. Because I'm thinking, well, okay, I'm trying to find 1 over a. I don't know what 1 over a is. I don't know anything about it. I shouldn't have to assume any knowledge of it. But now you're telling me that this iteration is not going to work unless I either choose my initial guess to be less than twice the value I don't know. And when I realized it, I thought, wow, this is a terrible method. Because you need such a highly accurate initial guess with knowledge of a solution. So I didn't really think about it again. But then, one time, some years ago, when actually I was having lunch at McDonald's right here with some fellow faculty, and one of them was one of our computer science professors here, Dr. Safar, who has since retired. And he said, being serious, that in his view, the best way of performing division was using Newton's method. Now, I didn't question him about it back then, but I thought, why would you think that? Because you need a good initial guess. And then I realized why he was actually right. Well, not necessarily because it's the best method, but I am now convinced that it is a viable method. Because you do know something about the solution because you're working with a floating point system. So let's suppose your number A that you have full knowledge of is this mantissa, and then times your base 2 to your exponent. So all of this is known. And your mantissa, if you're assuming like normalized floating point numbers, is greater or equal to 1 and less than 2, but you're in binary. So that means you actually kind of know something about the reciprocal. So 1 over a is 1 over n, now we don't know what that is, times 2 to the minus exponent. In other words, you know the order of magnitude of your unknown value, of your reciprocal. All right. Stop it. Oh, wait. Now, you don't know what 1 over m is, but you do know its range. It's between 1/2 and 1, excluding 1/2. So, here's what you can do. I'm going to choose my initial guess to be 2 to the minus x, negative x minus the exponent of a. Reason why is 2 over a is equal to this, where this mantissa is greater than 1 less or equal to 2. So if I choose just 2 to the minus e, I'm guaranteed, because notice, because this unknown mantissa is strictly greater than 1, if I choose my initial guess to be 2 to the minus e, I'm guaranteed to be less than 2 over A. Guaranteed. So, the floating point number system, its representation of A, hands me a viable initial guess on silver platter. So that I can use that and carry out Newton's method. So questions about that freaky example? Yes.
So, okay, now that we talked about this and the final is, final exam is approaching.
Yeah.
Do you think there's a possibility that we'll have a quick example on
No. You want one?
the Tom says so.
But yeah.
No.
If anyone, this is less related, but I don't know if anyone else is having this problem, but I cannot get to your website.
Oh, yes. I discovered this yesterday, but I could not get to my own website.
And I like you up through the USM faculty thing. I
Yeah.
just can't get to you.
Yeah. So when I saw that happen, yeah, I'm pretty upset about it. I emailed Dr. Schroeder and Dr. Kosopoulos, like, was there some decision to take this offline? Because some people or webmasters around here might not like us having these kind of sites or whatever. And Dr. Kosopoulos told me that it is a technical issue. Like there was not a deliberate decision to take this offline, but apparently the web people here have been cleaning things up and messed this up. So presumably it should be fixed soon.
Oh.
But yeah, this has been going on since yesterday, and I'm pretty miffed. Was something in particular you were looking for? Or
No, I was just trying to get there.
oh, okay.
I have the notes I need already downloaded.
Okay. Yeah. Yeah. At least for the class, everything's in Canvas. But yeah, it's like, 'cause sometimes I still go there because sometimes it's quicker. I always have that tab open. But now it takes you to the school website. It's like, oh, yeah.
Would you be willing to know, once you know it's up and running, send something on Canvas, so,
Yeah.
then everyone checking everything.
Yeah. Okay. All right. Now, so to summarize pros and cons of Newton's method. So the pro side, it does converge rapidly, usually quadratic. Also, even though we don't consider it in this class, but it will become relevant next semester for those of you who move on. For systems of nonlinear equations, Newton's method generalizes in a fairly straightforward way, which is not necessarily true of all methods. Newton's and fixed point extend quite nicely. Bisection, definitely not. Secant, it's complicated. On the downside, often you need a good initial guess, or Newton's method could easily diverge, as we just saw. Also, there's extra expense per iteration. You have to evaluate the derivative as well as f itself. So what can you do about that? Instead of using the actual derivative of f, you can approximate it using a difference quotient. If you have two of your iterates, xk and xk minus 1, then you can use a secant line approximation instead of a tangent line. And that leads to what's called the secant method. So what you do is, if I take Newton's method, but then here in the denominator is where you normally have f prime of xk in Newton's method. So you just replace that by this difference in quotient involving xk and the previous iterate xk minus 1. And then algebraically you can rework that and you get this formula for the approximate root. And that's called the secant method. So now you don't need the derivative anymore. So what happens is each new iterate is the x-intercept of the secant line that passes through these 2 points on the graph of f. So what you're doing is, now instead of approximating f by the tangent line, you have this linear approximation of f, and the slope is given by this difference quotient instead of the actual derivative. But presumably, I mean, if these roots are, if these x values are converging to a limit, then this slope should converge to the derivative anyway. So yeah, so still the same idea of approximating f by linear function, and then finding the x-intercept of that line to get to the next iterate. Just like in Newton's method, it's just which line you're using is different between the two methods. Now, the problem is each new iterate, xk plus 1, depends on the previous two. So it depends on xk, and it depends on xk minus 1. So in order to even get this method going, you need two initial guesses rather than one. So you choose x0 and x1. For those two, the secant method formula will give you x2, then x1 and x2 will give you x3, and so on. So there's that little hassle there. But it's worth it if you can, because each iteration of the secant method is cheaper than Newton's method. Newton's method, every iteration you have to evaluate f once and f prime once. Secant method, you only have to evaluate f. Now the order of convergence is not easy to derive. It's more challenging to do so than it is for Newton's method. It actually turns out to be this number, 1 plus the square root of 5 all over 2. It's the golden ratio. It has to do with, there's a relationship between each error and the product of the previous two errors. So if you look at the exponents involved, there's a Fibonacci type relationship between them that leads to this order convergence being the golden ratio. Now, because the order convergence is a number that's between 1 and 2, you say it's superlinear convergence. So there's a trade-off with Newton's method. So on the one hand, the convergence is not quite as fast. Now, superlinear is pretty nice. It's just not quite quadratic. But you have less expense. So it could very well be that the total time taken by secant method can easily be less than Newton's method. Because even though secant method requires a few more iterations, not much more, because each iteration requires less computational effort, you're only evaluating one function instead of two. Often, secant method is more efficient. So it probably is the most popular method. It's fairly easy to implement. Now, to give an example, with the secant method, okay, so here it is the same example, square root of 2. Again, still converging pretty rapidly. So in terms of convergence, it's still dramatically fast. So it's quite nice. Now, one thing that methods have in common, or two of the drawbacks. So convergence is still slowed down to linear if f prime is near 0 or exactly 0 at the root. Also, for Newton's method, the secant method both, you need a decent initial guess, or your iterates could easily diverge. So really the main thing that secant method buys you by replacing f prime with a difference quotient is efficiency. Yeah. One thing is to deal with the fact that you might have convergence called a safeguarded method. And actually, one of our own, Chandler Chimp, used this in her master's thesis, where you find an interval where a function changes sign, so you know there's a root in that interval. But instead of using bisection to get the root in that interval, because that would take too long, her method actually uses a secant method, where those endpoints are the initial guesses. And then if secant method produces an iterate that's outside the interval, that iterate is rejected. So then one iteration of bisection is performed, narrow things down a bit, and then you try secant method again. So that combination is guaranteed to converge, but it would converge more rapidly than just bisection alone. So that's a simple example of what's called a safeguarded method. So now here's one example of a safeguarded method. This is not the one that Chandler uses, but method of false position, also known as regular falsi. So what happens is, now the secant method would compute xk plus 1 using xk and xk minus 1. So whatever the last two iterates are, that's what's used. Regular falsi proceeds a little differently. It uses the last two iterates for which f has opposite signs. So that also is a way to guarantee convergence if you stay within the interval. But there's one problem with that, which is why we didn't use it. Why Chandler didn't use it is because that modification by itself can knock you down to linear convergence. It behaves in a rather infuriating way, to be honest. Because what happens is one of your iterates, like you're using 2 points each time. One of those points stays frozen, like it's always that point, and then only the other one changes, so it gets linear convergence. That can be fixed, and this is discussed in the text. Okay. Yeah, so there are improvements to root finding methods. Not a section I'm really covering, but I want to make you aware of it anyway. There's some methods to accelerate convergence. But for safeguarded methods, so this is regular falsi as described. It's actually a pretty simple method to implement code-wise. This is kind of reminiscent of bisection, but it uses the secant method formula instead of just computing a midpoint. But there's a modification that I present here in the Illinois algorithm that has this strange modification of taking a function value and dividing it by 2. And that actually fixes the logjam that regular falsi gets into. It's very strange. And it's easy to think that's cheating, or like how could it possibly work? But it actually does. And restores superlinear convergence. Okay. Yeah, so I want to talk a little bit about relationship between fixed point iteration and the secant method. Now, I talked about this before, but now I have more details. I have it written out here. So here's an example that I did last class with fixed point iteration, solving x equals g of x, and g of x is equal to cosine x plus 2. And just using straightforward fixed point iteration, you recall the iteration converged very slowly because the iterates kept bouncing back and forth between two values that were far away from the root. But this modification rapidly converged, where I take x and g of x and take the average. So I take the average of 2 consecutive iterates, that converged rapidly. And the reason why was that the function g near the fixed point has a slope of nearly -1. So having the x here basically canceled the -1 in the derivative. So what I did was generalize that idea that I performed this fixed point iteration, xk plus 1 is equals h of xk, and it's I'm taking a linear combination of xk and g of xk, so 2 previous iterates of regular fixed point iteration. So the idea is, if g prime at the root is approximately m, then h prime at the root is roughly 0. Now, we don't know what m is, of course. So we try this idea. Oh, I'll just use an approximate m, a slope of a secant line in here. And that's when I thought, when I thought of this, like, oh, I have a new root finding method. And then I proved that it converges superlinearly. I proved that this is your convergence, and that made me suspicious. Because I thought, oh, I just came up with a root finding method and found this order convergence. was exactly equal to the rather strange number that is the order convergence of the secant method. Like, did I just rediscover the secant method by accident? And I discovered that I did. Never mind. So, it was an adventure though, it was fun. Until the heartbreaking end. So, okay. Although, I feel like something like this would be useful in a teaching sense or something. About root finding. Okay. Or a different way to like present secant method or something. Okay, so that's root finding for you. In a nutshell. Okay. So, are there questions about any of this or homework or?
When we're discussing the pros and cons of names.
Yeah.
On cons, not as reliable, initial guess, not close.
Yeah.
But isn't right before that, you kept saying like that it's guaranteed to have a viable, guess. To have a viable guess using the, thing right before.
Oh, for this example. These pros and cons are for working with, talking about root finding in general.
Okay. So why is it so then one example is what it,
Well, for example, consider the division example where I chose the initial guess to be 1, which wasn't terribly far from the actual root, and the whole thing went haywire. So that's the sort of thing that, because on the one hand, you have your reliable but slow methods like bisection, where something like that would never happen. Then you have your fast but less reliable methods. There's a theorem, I think it's called Torovich's theorem, about how if the initial guess satisfies certain conditions that it can be proven to converge. But yeah, it's like, when I talk about the examples where Newton's method is used and only one iteration is performed, that's a situation where you're solving like a differential equations. You're time stepping. So you're at a certain time, Tn, and you're trying to get to a new time Tn plus 1, where those times are close. So you already have like a built-in initial guess, your previous solution, because your solution's not going to change that much in a small interval of time. So it's perfectly fine to use that as an initial guess. And one iteration will work very well. So under certain circumstances, Newton's method can be reliable, but for general purpose root finding, you gotta be careful. Like suppose you have a fairly high degree polynomial, and you want to use Newton's method to find like all the roots of it. But considering how polynomials can behave when they start swinging wildly, yeah, you're in for a rough ride if you do that. Questions about anything?
Are you gonna do a review Thursday?
That's all I'm gonna do on Thursday. Yeah, there's nothing left. Yeah. And I guess there's nothing left today either, so okay.
so this is the one that you should have put at the very end, and we are done.
What?
So this is the one that you should have put at the very end, we are done.
Oh, yeah.
Cause I think there's one other time you said we were done.
Oh.
And you weren't sure why you would type that.
Oh, okay. Hello.